to find the roots, right? So I can set up the characteristic equation. That's the same thing as taking the denominator of the transfer function and setting it equal to 0. So I can find those two roots. And then based on those roots, these next couple slides are going to talk about what we can expect for those roots. So here we go. There it is. So from the characteristic equation, I'm going to find my roots. And the roots will always look something like this. Now, they might have a piece missing, but there's going to be some kind of real portion, maybe, typically, and some imaginary portion, sometimes. So if I did the quadratic formula or use polysymbol 2 to find that with my calculator, it spits out the roots. And this is kind of what the roots look like. If I had a real term and an imaginary term, that A is like what my e to that root is. That's going to be dying out. And then omega, that ties to the imaginary portion, that gives me a frequency. So I have a sine and a cosine where these are dying out over time. So a lot of roots can be complex. If I don't have an omega, there's no sine or cosine. So I just have kind of a first order looking system. Just e to the negative something t. It's dying out over time. If I just had omega, this goes away. So my output is just going to be a sinusoid, basically. So it's all dependent on the roots. That's what we'll cover today. So let's take a look at what it looks like. So we're going to look at the 4 different cases. Case 1 is real and distinct. You don't have to write this down. Again, I'll post these slides, but let's just say, here's my equation. I've got my quadratic formula. I find the roots. They're -1 and -3. So I don't have any imaginary part. So therefore, this is my root. So I'm going to have e to the -1t. I'm going to also have an e to the -3t. So this is going to just kind of die out. It'll look like a first order system based on those two roots. And we would call this stable. So it does die out to 0. So eventually this is going to reach a steady state. It will hit a final value and just stop there. So anything that reaches steady state is stable. Notice, by the way, this equation up here, the output side is all positive. That's what we've been looking for. We've been looking for a stable system this whole time. What does that mean? If it's all positive here, I have negative roots. And if I have negative roots, that means that I have an e to the -t, so that dies out. So as time goes on, this goes to 0. The homogeneous solution goes to 0. So one way that we can visualize it is on the complex plane. So on the complex plane, we've got real as the x-axis, imaginary as the y-axis. So in this case, with 2 distinct negative roots, here are my root locations. They're both negative. There's nothing imaginary about them, so they're just on this axis. And therefore, because it's going to die out over time, it's going to go to 0. This is what our homogeneous solution looks like. Is these are going to die. All that we're going to be left with at that point is a, well, the output could look something like this, where the homogeneous part dies off and then we reach steady state. We have a final value right there. So this would be stable. This could be y over time. So these graphs are just showing the homogeneous portion, like the transient part of the solution. If they reach a steady state, that would be stable. If they don't, then my output is not going to be stable. It's still going to be changing as time goes on. Okay, so there's a bunch of different cases. This is for negative roots. For example, let's say my output side is not all positive. If I had a negative there, what happens? Well, it changes my root location. So now I have a +1 root and a -3 root. So therefore, my homogeneous solution is going to have some kind of constant times e to the 1t. So as time goes on, this thing is growing. So that means it's unstable. So based on these root locations, that updated here. Based on the root locations, I have a positive and I have negative. Any real positive means I have an e to the +t. It's going to be growing. It's going to be unstable. And so the homogeneous, it just grows as time goes on. I am not going to reach a steady state. Okay, so that's why when we were doing Bo-Body, it's really important for us to find it to all be positive on the output side. That means I have negative roots, which means stable. So that's kind of a visualization of what's going on. Questions up to this point? These are just real numbers. We're about to hit some of the complex stuff. No? Okay. This one we don't really see too often, but you could have a 0 root. So if you have a 0 root, so if one root is 0, that just gives us a constant. This will not die out, but it will just be a constant. This will die out, so I'm left with a constant. We'll call that marginally stable. We don't see this too often, but for the 0 case, that gives us it does give us a final value for the homogeneous, so this will reach a steady state, some kind of final value. So we call that marginally stable. And then I just realized I had the mic behind my head. I don't know how well that's going to be, but this should be better, okay? Sorry, everyone. 2 real repeated roots. We don't see this too often, but if I have the same root, so if R1 and R2 are both -3, that gives me something that looks like this. So for repeated roots, I actually have a time in that equation. And this would, this updates. If based on those 2 repeated roots that are both negative, we will see kind of a bump here because time is a part of that equation, but it ultimately is stable as well. So again, negative roots, stable. If I had 2 repeated positive roots, that's going to be unstable because I'm going to have e to the +t. So that's any positive real roots cause a problem. But this is more of where we're going to see a lot of our roots for underdamped systems. Typically, any kind of mass spring damper system, they are underdamped. And that means that I have complex roots. So let's say I've got an equation like this. So I set up the characteristic equation. I find the roots using my calculator. It's -2 ± 5i. So what that's going to become is that's going to become the e to the -2t's, because that's my real part of the root. And then I have a sine and a cosine of that 5t. So omega becomes the frequency, and then the real part, a, is my e to the negative, whatever that value is. So that tells us it's going to die out if it is negative. And what this shows us is that this is going to be dying out, so it will be stable. It will die out as time goes on, but now I have oscillations. So there's going to be a frequency, there's going to be amplitude, and some kind of frequency. And so it's going to look like this. So these are typical root locations. I have some kind of negative real, plus or minus. I've got my imaginary term here that's on the y-axis. And so that homogeneous response is going to have oscillations based on that frequency. Again, this tells us it's going to die out, it's stable, and this is the frequency that it's oscillating at. So we can learn a lot about a system just looking at that mathematical model. That's what we'll talk about today. Now, what happens if I have a negative? Well, if I have a negative somewhere in this equation, I can get a positive root. So that means I have an e to the positive 2t, and this will grow. So this is the root location that's going to grow like that. Let me give you an example of a unstable system. Have you ever put a microphone in front of a speaker? You have? Now, most of the times we do it accidentally, right? But then we find out really quickly this is not a good thing to do because it's unstable. It's an unstable feedback loop. And so as the microphone's picking up the speaker sound, that's going back through the speaker, and so it's growing. It's growing. The frequency, it's growing, it goes out of control, right? That's why you want to always move that microphone. That's an unstable system. Based on the way that it's set up, it's just feeding into itself. And so in that case, the mathematical model would have a negative part, giving us a positive root. Okay, the last one, we don't see this too often, but we could have a zero real part. This would, we would call it purely complex. So if my roots are, I just have an imaginary term. This would be my omega. I don't have a real part, and so that would just give me a sinusoid. I don't have an e to the negative anything. It's not dying out. And they call this a harmonic oscillator. So these are the root locations. And I will just be oscillating. There's never a steady state being reached, but they do call it marginally stable because it's not growing. It's staying at that same oscillation. So this would be like a pendulum if it was like an ideal pendulum without any damping or anything. Like it's just going to go on for a long time, right? That's really what's happening here. If we had that, just no damping, nothing going on, no wind resistance, it's just going to keep on going forever. The vacuum. Okay, those are the root locations. That's just a little introduction because that helps us. The first thing we always have to do is find the roots. Once I find the roots, that tells me a lot about how the system is going to respond. So we'll dive into it a little bit more today. But just in conclusion, if all the real roots are negative, the system is stable. If any real root is positive, that's right here. If this is positive, it's unstable. And any imaginary root, so any omega that we get, will have an oscillating response. So that's typically what we see for like a mass spring damper. There's going to be some oscillation until we reach that steady state. Questions? Okay, cool. So let's talk about a few other new things. This is on the equation sheet. This is the standard form for a second order system. And we're going to talk about these new characters. But always, we want to put this in standard form first. If I don't do that, I'm probably going to mess up some things. So I always want to get the y double dot, second order derivative, by itself. So no constant, no multiplier. So once we have it in this form, we're going to talk about what some of these things mean. So this is zeta. This is the damping ratio. This is how much damping we have. And then omega n, that's the natural frequency. Every system has a natural frequency. A lot of times we're trying to avoid it with our input, but it tells us a lot. We'll get into it more. So usually I can find the natural frequency first once I have it in standard form. Okay, once I have a number here, take the square root, I find the natural frequency. Then we can plug that in here, we can find zeta. And from those two, we can find a lot of information. We can figure out the settling time. We can figure out how many oscillations we're going to have. We can figure out the maximum overshoot. There's a lot of different things we can calculate once we know that value. Okay, so always put it into standard form first. Basically, the transient response of the second order system is characterized by these two variables. So once I have it in my standard form, I can find this frequency, then I can find damping ratio, and those are the only two things I really need to find. So let's just say you don't have to write this part down. I'll get to some equations soon, but let's just say I have a mass spring system. There's no damper, there's no friction. It's just an ideal. I have a mass on the spring, and I push it down, and I let it go. What's going to happen? It's just going to oscillate. There's no damping. There's nothing. So it's just going to have a nice frequency and everything. So if I put it in standard form, that would be this. I divide both sides by mass. And if I wanted to find the natural frequency of that system, then I'm taking the square root of this value. Because now I have it in standard form. So natural frequency is the square root of K over M. That's the undamped natural frequency. This is the natural frequency of a mechanical system, a standard MBK system. Now, as far as the frequencies we're going to see, they might be slightly off from that, but this is the natural frequency I get. If there was no damping present, this is the frequency that object's going to oscillate at. So if I increase the mass, the frequency goes down. If I increase stiffness, the frequency goes up. So that is the natural frequency for a standard mass spring system. I can use this even if there is damping. I can still find the natural frequency. It's still going to be equal to this. It's always square root of K over M for an MBK system. And we'll get into some of the other parts like resonant frequency, but this is kind of an important characteristic. We're typically trying to avoid this frequency. If I give it an input, I don't want to get close to the natural frequency. All right, so that's mass spring damper. We didn't do this. We didn't do a pendulum. I talked about a pendulum a little bit. If we had an ideal pendulum, you don't have to write this down either. If I put this in standard form, and some of these things can kind of cancel out, like the mass doesn't matter. So we can take the mass out of there. These lengths can kind of cancel at least one of them. If I put it in standard form, that gives me this. So the natural frequency is going to be just the square root of G gravity over length. Length is the only thing that matters for a pendulum. So if I don't have any friction or anything, that gives me the natural frequency, and we can find like the period of the oscillation from that. So it's very similar to like that mass spring. What's going on? Where gravity is really the thing that's driving this pendulum. Anyways, I just want to put it in standard form, and then the square root of this tells me the natural frequency. Okay, the other thing, you don't have to write this down. I did not. Man, it's slow today. You don't have to write this down, but the damping ratio, okay, once I solve for the natural frequency, I can then plug that in here, and there should be some kind of number here. And from there, I can solve for zeta, the damping ratio. And the damping ratio is really helpful because if damping ratio is equal to 1, the system is critically damped. That means there's no oscillation. So there's a lot of damping, enough that it's going to be a smooth curve. There's no oscillations, anything like that. If it's less than 1, the system is underdamped and there will be oscillations. And if it's greater than 1, the system is considered overdamped, which also means no oscillation. So basically 1 is kind of the breaking point. If I'm less than 1, I see oscillations. Once I hit 1, that's critically damped. Anything greater than 1 is overdamped, and it's just going to be a smooth curve for that output graph. Most of the time, we're dealing with underdamped systems. If you think about car suspension, that's like a major one. We want to make sure it's underdamped. We don't want to feel all the different things. We want there to be a little bit of give in the system. So we're typically dealing with underdamped systems. Okay? So that's how we find the damping ratio, make sure that we have it in standard form. So I just want you to get some practice real fast. This is my second order standard form. Let's say I have this equation right here. We use Bobati. We have some values here now. I want you to find the damping ratio and the natural frequency and determine if it is underdamped or not. The first thing is always put it in the standard form. We'll go to that police. Maybe our break we go check out. What's going on? My office starts with cancel. No, it's not correct. Because we're trying to find natural frequency, trying to find damping ratio. The first thing is we want to divide both sides by 6. That gives us standard form. So we'll have theta double dot plus 11 over 6 theta dot plus, we could say 50 over 3 theta over 80 over 3. On the right hand side, just make sure you always divide both sides by the same number. And then now I have it in standard form. So this is equal to 2 zeta natural frequency. This is equal to natural frequency squared. So we can find those values. And the frequency, the natural frequency is going to be in radians per second. Most of our stuff, we're just dealing with radians per second. Gotta get my notes out. I don't even have these notes. So I got a natural frequency of 4.083 radians per second. Anyone else get that? You graphed it? So that's always the first thing you want to find is, that's just, again, standard form, that final term multiplied by theta, that constant is my natural frequency squared. So natural frequency square root of 53. I get this like that. Frequency. Then once we have that, we can plug it into the other number to solve for the damping ratio. So 2 theta natural frequency, which is what we just found, 4.083, is equal to 11/6. So then we can solve for zeta. And I got 0.225. The damping ratio is unitless. It's going to be a number, it's a ratio. So you don't need any units for this guy. Now, my question is this system underdamped, critically damped, overdamped? What? Overdamped? That's one of the options, yeah. What would you say? Is it less than or equal to or greater than 1? It is less than 1. So this is less than 1. So therefore it is underdamped. Absolutely. And that's typically how these systems are. They're going to be underdamped. Not always the case, but usually the case. One thing I want to do real fast, I want to show you some of the roots. We were talking about the root locations. If it's underdamped, what does that mean? Well, if I created the characteristic equation for this, so we have r squared plus 11/6r plus 50/3 equals 0. That's the characteristic equation from here. You could do it with s's as well. It doesn't matter. Roots, poles, same thing. So if I plug that into my calculator, because I don't have it in front of me. So again, in your TI, you can do polysymbol 2. You can do a polynomial. This is the second order polynomial. We have a 1. We have 11/6. And we have 50/3. And it'll spit out the roots. And the roots are complex. It is negative 0.92 plus or minus 3.98 I. So if you remember what we were just talking about, the output is going to have oscillations. How do I know it's going to have oscillations? because I have a frequency here. That's my 3.98. And then we have an e to the negative 0.92t, which means that transient part is going to die out. So this is what an underdamped system looks like. It's got roots that are complex, negative, real, complex, so they have oscillations until they reach a steady state. That's what underdamped means. So if that polynomial changes enough where I get an overdamped system, I'm not going to have oscillations. I'm just going to have real roots in that case. So it's okay if you don't understand it now. This is kind of our introduction today, but that's how all these things sort of connect. Questions? Nothing? All right. But standard form. Always put it in standard form. That's going to save you a lot of headaches down the road. So now we're going to talk about underdamped second order systems. So if you have an equation sheet, great. If you want to pull it up on your computer, that's also good. We're going to walk through. The equation sheet has a bunch of equations, but they only work for underdamped second order systems. So if I were to find the damping ratio and it's 1 or greater, I can't use these equations. That's what this warning sign is for. Okay? This has to be less than 1. If it's less than 1, we can use all these equations we're going to talk about. All right, where is my equation sheet? Somewhere. Here it is. So on the equation sheet, there's a whole basically page of equations, and all of them use the damping ratio, theta, and the natural frequency. Like, they're just scattered throughout. There's a bunch of equations there. So once we find those two, we can figure out a lot of stuff about this output. Like, what is the graph going to look like for the system? So the first one we'll talk about is damped frequency. This is the actual frequency of the response. It is based on the natural frequency and the damping ratio. So, for example, if I give a mass spring damper a force, I hit it, it oscillates, and this is the output graph. The frequency that we see is not the natural frequency. It is the damped frequency. So it's a combination of the natural frequency and the damping ratio. Okay. If damping ratio is 0, that means I have no damping. Then these two are equal. That's great. If damping ratio is 1, which means it's critically damped, then the damped frequency is 0. I have a lot of damping. It's just going to be a smooth graph at that point. But obviously, this is for underdamped systems. We can use this. This is our frequency that we can find from the graph. So with a lot of damping, they're going to be pretty different. If damping is very small, then the damped frequency is close to the natural frequency. So you don't have to memorize these equations. They're on the equation sheet. Once I have these two values, I can figure this out. Does that make sense? One person, two people, 3 people nodding, maybe. Okay, that's 50% of the class, by the way. Performance criteria. Let's see. So I have it in standard form. These are other equations on the equation sheet. So, for example, once I know the damped frequency from that last slide, I can take 2 pi radians over that, and that tells me the period, which is I can look at either peak to peak or valley to valley. Typically, I start at time 0. So the period would be from time 0 to the time when I hit that first valley. So from valley to valley, that is 1 period of oscillation. That's just 2 pi radians because that's 2 pi per cycle divided by the damped frequency. Another thing, so again, that's on the equation sheet as well. And we also have the peak time. So this is actually half of the period is when we're going to hit our highest peak. We'll talk about how to find that value. But if I wanted to know the time, that's just t over 2. Pretty easy. Or it's, this equation and this equation kind of combined. You just take the 2 out of there. And so it's pi over that equation right there. So again, everything comes out of the natural frequency and the damping ratio. I got to find those things first. Then we can plug that in. So this would be the time where we hit that highest peak, or 1/2 of the period. And we'll do a problem too. So hopefully that kind of brings it all together. Second off, if I want to figure out that maximum peak, that is part of the equation that's called maximum overshoot, or percent overshoot. If I want to find it and I have the damping ratio, I can throw the damping ratio in here. That's going to tell me my maximum overshoot. And so it's a pretty complicated, this can be kind of hard to plug into your calculator. All of this in parentheses is what we're taking e to that power. So it's going to be damping ratio pi, negative, divided by this. And then we're taking e to that negative power. And that's going to give you a percentage. It's going to give you a decimal. But what that's going to tell us is how far above steady state this first peak is going to shoot over. And so another way we can calculate this is y max minus y steady state divided by y steady state. That gives us a percentage that this is going to go over. So if I find the maximum overshoot based on this equation, all I do is add it to 1, and then I multiply it by my y steady state. So wherever we end up with, this is how high above that first peak is going to be. We'll do a problem, so hopefully that kind of ties it together. But settling time is a little bit different than first order. Settling time is equal to 4 time constant. Still is, it's just now I have a different equation. I don't actually have a time constant within my equation. So this is the settling time. It's going to be 4 over these two multiplied by each other. And so that's going to tell us, in this case, it would be somewhere within 2% of its final value. Good. Use the equation sheet. Once we have those two things, we can kind of piece this together. This is going to just tell us, obviously I can simulate it in MATLAB and so forth, but being able to understand, this could be a really important thing. We don't ever want to overshoot by this much. Okay, so based on our equations, based on our mass spring damper, are we going to hit that? And then how long is it going to take for us to reach steady state? Those can be some important factors of figuring out what your components should be. Another thing is number of cycles. So this is another equation that involves the damping ratio. This is going to tell us how many cycles we have before we reach steady state. How many cycles, just looking at the graph, how many cycles there are? 5? Because we start time 0. So I can look at from valley to valley is 1. So this would be 1, 2, 3, 4, yeah, maybe about 5. Maybe a little bit less than 5. It could be 4.7. So number of cycles is just going to be a decimal value. It's going to be, maybe it would, if I calculated, it would be like 4.8 or something. That's the number of cycles we have before we get to within 2% of our final value. And then the other thing that's really important is, well, we need to figure out where is our steady state value. Like, if I don't have the graph in front of me, but I have the equation, how can we solve for the steady state? Like, how can I find y steady state? Is there a way we can find y steady state you say DC gain? No. Okay. We talked about DC gain in the last class. I could make a transfer function out of this. I could set all the s's to equal to 0. That's the same thing as saying all the derivatives go to 0 because s is, dot becomes s, double dot becomes s squared. If all the s's go to 0, that means all the derivatives are gone. And what that means is that once I reach steady state, there's no more derivatives. It's not changing as a function of time anymore. It's just one constant, right? So for a steady state response, we can say, hey, this goes to 0. That y double dot goes to 0 and y double dot and y dot go to 0. I'm left with this equation. So y steady state is equal to a, whatever that constant is, divided by the natural frequency squared times whatever my input is. Now the input in this case must be some kind of constant. For us to reach a steady state, this input has to be a constant or a step. So once I have it in standard form, I have this term here. Oh no. Oh no. This is, why did I do all this work? It was already there. So that's our equation right there on the equation sheet. So once I know the natural frequency, and again, I have to have it in standard form. This A is not what the mathematical model starts with. It's when I put it in standard form, what is that constant right there? That's the A that we're going to use. This all has to come from standard form. All right, so let's do a problem and then we'll take a break. Or you know what? No, you're going to do this first, then we're going to do another problem together. It's a little bit harder, and then we'll take a break. So let's say we have this equation. I want you, oh, this is the same one we were working with last time in class. So this is second order. Now I want to find we already found the roots to this. They're both complex. We want to find the natural frequency damping ratio and the output, steady state output, if the input is a step of 10. Put it in standard form. How do you put it in standard form? Yes, if you divide both sides by 2. Step 1, put in the standard form, divide both sides by 2. And after that, you want to find the natural frequency, you want to find the damping ratio. And then lastly, we want to figure out what that final value is. What is y steady state? If you have questions, let me know. Okay. That's first standard form. So always put it in standard form first. Save you a lot of trouble, even in the next couple of weeks. Who's got a damping ratio? Should be less than 0.5, I believe. 0.4, really? Wow. I guess that makes sense. Which is less than 1. So this is an underdamped system. That's good. So that's how we find the natural frequency of the damping ratio. It is underdamped. We already found the poles before, if you remember. They were negative real complex. So that means there's oscillation. So it is underdamped. The last thing I want you to find is the steady state, Y steady state of the input. And if you need this equation, it's right here, which is on the equation sheet. So Y steady state is equal to A constant times the input divided by natural frequency squared. Or you can use DC gain to solve it. So from the equation sheet, Y steady state is equal to A times the input divided by natural frequency squared. Yeah. What is that? So the input is a step of 10. We're just going to evaluate it as a step of 10. What? So U is equal to 10. Did you get a Y steady state? Y steady state is 1.5. What'd you get? 1.5? I don't know if it's the right answer. What'd you guys get? Do you have a Y steady state? 0.75. Whoa, there's like a 2 multiplier going on. Let's double check this. First off, what is A? Three over 2. or 1.5. I think maybe we got to be careful. This is my standard form. So this is my A. That's my constant when I have it in standard form. So this is going to be 1.5 times the input, which is a step of 10, divided by the natural frequency squared, which is equal to 20. So this becomes 0.75. That is my steady state. And if this is mechanical, then that would be meters. So there should be some units to this, but that would be my output. Now notice this is also the same thing as saying, 1.5 times the input divided by 20. That's my y steady state. I could use this old non-standard form, but why? I could take 3 times 10, so that's 30 divided by 40. So you can still find it without being in standard form. Just make sure you don't mix up the two. Okay. Questions? Yeah. The characteristic roots are the poles. Yeah, they're the same thing. Poles of the transfer function. If I have the numerator or denominator of the transfer function set equal to 0, that's the same thing as the characteristic equation. Yeah. All right. You know what? Let's do this problem after lunch or break. What? The lunch time, Lori? Let's take 5. So it is, wait. So at 8:13, we're gonna do a problem, and then we're gonna go in reverse, and then you'll have some time to work on your lab. Cool. 8:13. Let's check out the thing. What? Eight. Eight 15. It's cool. Yeah, I mean, especially that early in the morning. Yeah, that's probably true. Yeah, you're right. You're right. Uh, yeah. You didn't get any free stuff? Yeah. They didn't offer enough? All right. Well, welcome back. This is example 7.8, and this is a rotational problem. And these are supposed to be thetas, but sometimes PowerPoint cuts them off. So what we want to do is sketch the step response of the rotational mechanical system as well as we can. That means finding, some of those important things we were talking about: settling time, maximum overshoot. We obviously want to find where the steady state value is going to be. So there's a few things we got to do here. So let me move that mouse. It's kind of in the way. What should we do first? Well, body has been done. I have the mathematical model. My goal is to be able to figure out some of the important parts of this. Like, is it underdamped? I don't even know if it's underdamped. Maybe we won't have oscillations. First step, standard form. Thank you. So what should we divide both sides by? 0.2, or multiply both sides by 5. So standard form, we're going to have theta double dot plus 8 theta dot plus 325 theta equals Tn. Are you okay? Ouch. Everyone good? You okay? Yeah, you're fine. Okay. Yeah, it looked like it hurt. Okay, so we got standard form. Standard form. Now we can start looking at what's like our final value. Well, first off, we probably want to find natural frequency damping ratio, because those two will kind of go into everything else. Now, what did I do wrong with this equation? Because it's not right. Should be 5Tn. Thank you. I did leave a little bit of space, so there it is. Yeah, make sure we do it on both sides. That's going to play a big role here. So this So 325, so natural frequency is equal to the square root of 325. That's going to give us our value in radians per second. We'll do that in their head real fast. 18, we'll say 18.03 radians per second as a natural frequency. Now that's not, like we talked about, that's not the frequency we're going to see necessarily there for our output. That's just the natural frequency if we had no damping. And now we can put that into the 8. So 8 is equal to 2 times zeta times the natural frequency, which is 18.03 radians per second. And so that can give us our zeta. And that should be pretty small. See, I have 0.222, which is less than 1. Therefore, it is underdamped, so we can use all the equations we've got. Okay, so first put it in standard form, find these two. After that, we've got an equation sheet full of equations that once it's underdamped, that's great. I can use all those equations to figure out, some of these values. And I can really start anywhere. It doesn't really matter where we start. But one thing that might be helpful for us is to figure out the steady state value of theta. So what is theta steady state? Where's this thing going to end up with? Yeah. Okay. Yeah. I do. Yeah. Most of the systems are underdamped, especially ones that we look at too. Yeah. But we can talk about it more, I guess. So theta steady state, I have this equation where it's A times U over natural frequency squared. What is A in this case? It is 5. This is A right here. What is our input? The step of, so it says we have a step input of 2.5 Newton meters. Oops, Newton meters. And then over here we've got natural frequency squared, which is 325. This is going to give us an output in radians because it is rotational. So we're looking at theta steady state. So this is 12.5 over 325, which is 0.04. Give me another decimal. Cool. 0.038 radians. All right. So that is helpful. Now it says that the system is initially at rest before this happens. So theta at time 0 should equal 0, basically saying that there's no initial conditions. So this thing is going to start at 0. It's going to oscillate because we know it's underdamped based on the input. It's going to start at 0, it's going to oscillate, and then the end point is 0.038 radians. So that's kind of where we're at. Now we need to fill in a little bit more of those details. Questions? Okay. You know what? Let's just calculate while I have some space here. On the equation sheet, there's an equation for settling time. That's 4 over zeta times natural frequency. So now I can piece together even a little bit more of that, what that steady state is going to look like. When does that steady state happen? That's going to be at the settling time. And so we can plug in our values here. So this is 0.222 times natural frequency, which is 18.03 radians per second. 1.0? Oh, wow. So we'll say it's 1.0 seconds. Cool. So now we know this value, the final value, we know that the settling time is going to be 1 second. That's awesome. This is an example from the textbook. They would make it like that. End of the second. Okay. So the next step on the next page is, okay, we know this, the steady state stuff. Now we're going to use natural frequency and damping ratio to figure out that transient portion, like what's our maximum overshoot? What's our max peak? What is our damped frequency? What is the frequency we see here? What's the period? So those are some of the things we need to fill in next. Questions up to this point? Okay. So again, natural frequency is equal to 18.03. Damping ratio is equal to 0.222. And now I can kind of go down in the equation sheet. The first thing I have is maximum overshoot, which is equal to E to the negative zeta pi over the square root of 1 minus zeta squared. So we take E to this power. We're going to plug in zeta, which is 0.222, into this equation. And that should equal 0.498. So what this means is that the peak, the max peak, the first peak, is going to be 49.8% higher than my steady state value. That's what that maximum overshoot means. It's a percentage. 0.498, 49.8. So that means that we're overshooting that first peak of the graph is going to overshoot the steady state value by about 50%. That's what that means. And so if I wanted to find, we can use this, basically my theta, my peak theta is going to equal theta steady state times 1 plus that maximum overshoot. So we have 0.038 radians times 1 plus 0.498. And that's going to give us what our peak value is going to be in radians. So it should be 50% higher. Not exactly 50. Close. So 1.498 times that gives me a peak of 0.058 radians. Okay, 50% higher. Now, this is a little bit harder to understand. The maximum overshoot percentage, using the equation sheet, we're just using the damping ratio. We can figure that out then solving here. This is kind of the method. to getting to it using the equation sheet, rearranging some of those parts. Do you have any questions about this, what was just done? This is that first peak. This is going to be the y on the y-axis. This is my value, 0.058. That's as high as we go. Then it's going to oscillate until we get to our steady state, which is going to happen at 1 second. Good. Okay, so the next thing is, if I go down the list, TP, which is the peak time. So where does this peak happen? This peak happens at, this is pi over natural frequency times square root 1 minus damping ratio squared. So if I plug in my damping ratio, if I plug in my natural frequency, for this we get 0.178 seconds. Okay. We already found settling time. Now, period is basically the same equation, but times 2. So the period is really just 2 times my peak time. And remember, period is like from peak to peak, or from valley to valley. This would be 0.356 seconds. That would be one period right there. Okay. Peak time is half of that. Another thing that we could find, if I go down the list here, we could find the number of cycles. Now, I can kind of estimate number of cycles. If my period is 0.356 seconds, that's what it takes to go from one valley to valley. And then if my steady state happens at 1 second, that means my number of cycles is going to be a little over 2.5 or something. Because it's only going to go through about 2 point some cycles before we reach our steady state. So, and we have this equation here, which is 1 minus this over pi damping ratio. This is also the same as settling time over the period. So if I take 1 divided by 0.356, that's just 2.81 cycles. That's how many cycles we're going to hit before we reach steady state. And then I don't really need this, but just to show you, we can calculate. This is also on the equation sheet. Damped frequency is the same as natural frequency times 1 minus zeta squared. This is equal to, wow, I don't have this. We have 18.03 times. This is 17.58 radians per second. So natural frequency is 18. Because we have some damping, it's pretty light damping. Our frequency that we see on the output is slightly lower. All right. So we're gonna tie this up now. I've done everything. I've gone through the equation sheet. I just have all these values. But what does that mean? Well, my goal is to figure out, we've figured out all the important stuff. Like, let's get these values. But what does that actually mean from a graphical standpoint? So I'm going to take all of these and put them on a graph just to show this is what we expect the system how to respond based on the variables we have, the values we've got, and the step input of 2.5 newton meters. Before I draw it, are there any questions about this slide? Okay, so here's the sketch. This is time in seconds, and this is theta in radians. We're going to start at 0 times 0, and I know that my system reaches steady state at 1 second. I know that my steady state value is 0.038 radians. So that was what we pieced together on the first part of, okay, this is my final point. This is going to happen here. So at this point, that's where we're going to reach our steady state right there. Now, how we get there, because this is underdamped, I'm going to have oscillations. So my peak, if I break this up into 50%, 50%, this is like 0.058. This is my peak value right here. So we're going to hit that peak somewhere within the first 0.2 seconds, basically. So we can break this up. This is seconds, something like that. Okay, the peak time is we found it to be 0.178 seconds, which is probably somewhere right here. This is peak time. That's where we're going to hit our peak. So this is just kind of how I kind of piece it together, let's look at steady state first. Now let's start with this. And what's going to happen is that these peaks are going to converge. So I can kind of make a trumpet from here to there. So I'm starting at 0. These waves are going to get smaller and smaller until I reach steady state at 1 second. My period is 0.35. That would be maybe like here. So from here to here is 1 period, 0.357 seconds. And then I can kind of piece some of this together. Based on that same period, I'm going to move the same distance when I set up this graph. So it won't be perfect, but at least we're getting the idea of it. So to draw it, I go up to the first peak, come down, that's 1 period, go up, down, then we reach steady state. So that's kind of how we draw it. It's not perfect. Really, my cycles is 2.8. I maybe almost get to 2.8, but that's our oscillations right here, going from maximum peak to steady state value, all happening at 1 second is our steady state. Okay, so these sketches don't have to be perfect, obviously. Most of it is just like finding the important values, but do we really know how the system's going to operate? That's what we see in Simulink. Like, it's all based on these numbers, right? Putting in these numbers, we give it an input, and then it's calculating how that's going to work. So the graphs that we see are, based on all those numbers, if we change some of those, that's the same calculation that's going on for their graphs. Okay, questions about this? Any questions? I got one last thing I want to cover, and then we'll do a quick example, and then you'll have time to work on the lab. But everything today is all about second order systems. So if I have a second order, first put it in standard form, then we can find some stuff. We can actually estimate the sketch, and then we'll now talk about the reverse, which is called the log decrement method. We're still here, but what we were just doing is approximating a sketch based on an equation and an input. We can also go the opposite way. We got a double arrow here. I can look at a sketch. So if I do some testing and I get I have some test data for that, we can actually approximate a second order system from that graph. So I'll show you how we do that. It's really just one equation that kind of lays the foundation. Okay, so if I have an object, let's say, or it's a spring and damper system, kind of like those shock absorbers, K is pretty easy to find. Hook's law. I can just hang a mass from it. I can figure out the K value. Mass is pretty easy. I can put it on the scale, figure that out. The hard thing to find is typically the damping coefficient. So to find B, that coefficient, we have to perform some kind of dynamic. It's impulse response. So you give it a short, sudden impulse, and you see how the system responds to that. That's how we can find B. In fact, that was one of the capstone groups about 2 years ago. They were actually trying to create a system, which I think is just over next door, where you put an object in there, you give it a short impact using LabVIEW in MATLAB. Can you believe that? And they built their own circuit and everything. But based on that input, then you read, okay, what is our output? And from there, we can actually create a mathematical model. So we can find that B value, which is the hardest to find. So you don't have to write this down. I'm going to show you about 5 slides that kind of lay the foundation, and we get to our equation that we're going to use. So let's say we have the impulse. So I give it a quick hit. I take it away. So we see an oscillation like that, and then it returns to 0. The damped frequency is pretty easy to find. So if I know the period, which is just peak to peak, we can do 2 pi over the period that finds the damped frequency. So the impulse response, what I'm finding is that I have some kind of constant. I have the frequency. This is the oscillation, omega d, damped frequency. And I also have some dying out. So we're trying to figure out that damping ratio because this is an underdamped system. So I have complex roots like that. So now this looks fun. We're going to form the ratio. So to get a little bit better approximation, I'm going to look at peak 1 and peak 2. And so going from 1 to 2, I add a period. So you see here we've got the capital T in the equation. So as time goes on, as I add a period, I can create this ratio of peaks where we get a lot of cancellation. You don't really need to know this, but you can see there, right? It's based on the damping ratio and the natural frequency. So for those 2 peaks, I can determine, because I know the period, I can find at least what the damping ratio is and the natural frequency, what those are combined. Now we start doing a log decrement. So if I take the natural log, I can get rid of that E, and we can make some substitutions here. I'm not going to go too far into this, but we can solve for the damping ratio because, again, we're looking at peak to peak using the natural log. However, looking just at the first 2 peaks is not going to give me much of the story. So it's actually better if I look at all the peaks. So if I start with the first one and move all the way down, and that means that all of these different natural logs, as I go from one peak to the next, now there's a lot of cancellation, and we get this equation. So this is on the equation sheet. Basically, it's a very good approximation of finding the damping ratio based on a lot of peaks. So I'm not just the first two, but I can look over the peaks until we reach steady state, and we can set up to find the damping ratio. This is on the equation sheet. You're going to use it. Let's talk about it. There's a few things we need. First, there's N. That's going to be the number of peaks that we're talking about. And then we have an X1. And then we have an XN. So there's three things you need to fill this in, and they're used a few times. N is the number of peaks. Now, N is the number of peaks before we reach steady state. And remember, steady state to us is like within 2% of steady state. So I want to be careful. I don't want to just pick like the smallest thing I see. Like, even though maybe this one's a little bit, it's probably really close to steady state. That's not going to give me very good information. So I would probably either pick this one or maybe this one. The more data points we have, it's going to help us, but I don't want to get too close to steady state. So, for example, with this one, this would be my X1. This would be 2, 3, 4, 5, 6, 7. So I'd probably say N is equal to 7. Okay. So you get to pick. Now you can pick 6. 6 is probably going to be fine. It's going to give you maybe a slightly different damping ratio, and that's okay. We want to get close to steady state, but not too close. X1. Now these are also on the equation sheet. X1 is the distance from steady state to the first peak. So steady state for an impulse response goes back to 0. So this is pretty easy. It's just going to be this minus 0. So we can just approximate that to be, I don't know, 0.055 or something. And then Xn, which could be at this 7th peak, maybe we say it's 0.003 or something. If I had the data in Excel, it'd be really easy to pull, those peaks. We can still approximate it and get a pretty good value. But these are the values we're going to throw in here. It's always distance to steady state. So I put it in, I use the natural log, and we can solve for the damping ratio. And then again, damping ratio can help me figure out all the rest of it. We can go all the way back to M, B, and K using this damping ratio. All right. You okay with this equation? All right, we're going to use it. We'll do an example. So first off, I've already mentioned this before, but a lot of systems, they can be super complex, 100th order, 8th order, whatever. That system is going to have some dominant roots. So I can, even though I'm looking at a graph like that, it could be a really high order system, but we're just going to approximate it as a 2nd order, and we can get pretty close. So, even if the real thing is high order, nonlinear, I get an output. If that output looks like this, we can create an approximate model, 2nd order model that's going to do a lot of the same stuff. And so that can be helpful for us just to create a quick approximation and run some quick tests. So we're going to do this equation and we'll be done. This is our example problem. We're going to do it together. Our goal, let's say I've got this testing machine. I put in some kind of system. I give it a force of 10,000 newtons. So I'm hitting this thing with 10,000 newtons. It's a step input. And what I'm getting is a position in millimeters. So we're seeing that this mass spring damper system, moves, and it oscillates a little bit until it reaches a steady state. My first engineering job was guardrails for highways. So what we do is we put a post in the ground, like Ponderosa Pine was my first one, and you run a bogey into it. So it's giving you a force. It's like a step force pushing against that post. The post doesn't just move, it oscillates a little bit. So there's a little bit of until it reaches that steady state. And that can happen pretty fast, much faster than this. But based on that input, we're trying to figure out, even though I know this is a nonlinear, it's like if I'm looking at a post in the ground, there's a lot of things going on. But could we just create a quick approximation for a approximate mass, stiffness, and damper based on how it reacts to this input? That's what we're doing here. Okay, so we're just going to walk through this. I've got kind of the outline of where we're going because our goal is to find MB and K, but there's quite a few steps along the way. So the first one I got to ask is, what is the steady state response of X? What is X steady state? Cool. 48 millimeters. And let's just make sure we've got all consistent units. So I'm going to put 0.048 meters. Now we want to find the damping ratio. How do you think we find the damping ratio? That really long equation, the log decrement formula, absolutely. So for the log decrement formula, so we're trying to solve for the damping ratio. We need three things. We need to figure out N. We need to figure out X1. We need to figure out Xn. So how many peaks would you say there are before we get close to steady state? 5? This is our X1, 2, 3, 4, 5, 6. Oh, you could make the case for 6. Now this is, again, steady state is within about 2%, so that might be a little bit close. I think you can make the case for 4. At 5, we may have a sizable enough difference that we can use it. So we can say N is equal to 5. So then we want to find these peaks. Remember, the peaks, so these X values that we use for the log decrement formula are not the absolute value. They are with reference to the steady state value. If you do not do that, your damping ratio is going to be way off, and it's just not going to work. So what would you say X1 is? First off, what's the absolute value of X1? 80 millimeters. What's our steady state? We said 48. So this is 32 millimeters or 0.032 meters. It's always the difference from that peak to the steady state value. And then X5, what would you say that is? 50? Wait, what? Yeah, we would say, we could say 50 minus 48, 2 millimeters or 0.002 meters. This number, because we're so close to steady state, this number, whatever it is, I mean, if it's 20 peaks or whatever, it doesn't matter. This one should always be really small because I'm close to steady state. So if it's not really small, again, you want to make sure you're taking the reference to that steady state value. All right, so now I've got my equation. This is going to be, so if I'm following, this is n minus 1. So the equation is 1 over n minus 1. So that is 1 over 4, because we have 5 minus 1. Then I've got the natural log of x1 over x5 and then we've got square root of 4 pi squared. That's just 4 times pi squared. Plus, again, we've got the 1 over n minus 1, which is 1/4. Natural log. Again, we've got the 0.032 over 0.002. And all of this is squared. Now, what some people have done, because sometimes we see this and we use it quite a bit, is to actually program it in a calculator. Let's just ask for those two values. And these are all natural logs. So I got the bottom here is 6.3213. Then we have the numerator. It's this. So I got a damping ratio of 0.1097, which is less than 1. Did anyone else do it? You got it? You got the same answer? What'd you get? No, I could have messed it up. What'd you get? Yeah, just make sure this, all of this, 1 over 4, all of that gets squared. So yeah, that's what I got. So this is less than 1, so obviously we are on under band. We can see it. If I got something that was 1 or greater, obviously I plug something on. So that's another thing that you can check. But anytime I have really high oscillations, you can expect the damping ratio to be pretty small. So now that I've got that, and look, this approximation may be a little bit off. Maybe it's more like 1.5 millimeters. Maybe it's close to 1. It's kind of hard to see. That's going to change this a little bit, but it's okay. We can get a similar kind of equation here. So we're going to solve this together, and then we'll be done here. That's my damping ratio. That is zeta. But there's more stuff we want to find. Questions about this equation? Okay, just make sure all those are with reference to steady state value. The next thing I want to find is the natural frequency. And the damped, this will just be a damped frequency. Okay, I've had a couple people over the years try to figure out what's the best way to do this. Some of them have thought, now that I know the damping ratio, maybe I'll use settling time. I don't like how much uncertainty there is on settling time, because some of you might think it's like 8 seconds, some of you might think it's 10 seconds. That makes a big difference. It makes a big difference. So I don't think settling time is a very good use of this. We could look at damped frequency. Damped frequency is equal to 2 pi over the period. So if I know what the period is, I say 2 pi over that, that would give me the frequency of this oscillation, which could be somewhat helpful. So what would you say? This is a little bit easier, I think, than trying to determine what that settling time is. This would be about right here. That would be 1 period. So we can estimate that and then figure out the damped frequency. What would you say that number is? My lines might not even be that great. I didn't really get out the ruler for this either. If this is 1, what would you say period is? 1.8? Yeah, sure. We could say 1.75, 1.8 seconds, whatever. So we're going to say 1.8. So if we take 2 pi over 1.8 seconds, that gives us a damped frequency of 3.49 radians per second. Now, damped frequency is on the equation sheet equal to natural frequency times square root of 1 minus zeta squared. So we can then solve for the natural frequency, which will, once I have that natural frequency and the damping ratio, then we can really work on what this equation should look like. So let's see, 3.49 is equal to natural frequency times 1 minus, what was our damping ratio? Okay, so we can solve for that. We can figure out the natural frequency from there. So we got 3.49 divided by square root of 1 minus 1.9. I got 3.51 radians per second. It should be small. It will be small. A small difference, right? Because damping ratio is so small, these two frequencies are basically the same. Like I have very little damping. We're very close to the natural frequency. Okay. So just as a recap, this is really important because that goes into my standard form equation. This is really important because that goes into my standard form equation. So really, to find MB and K, the main things I got to find first are, let me get to the damping ratio using log decrement formula. Let me also find the natural frequency. So for me, I think it's easiest to look at the period, find the damped frequency, and then work back from that. So now the question is, can we find MB and K? And again, this could be a really complicated nonlinear system. What we're trying to do is just do our best to, based on the data right here, based on the graph, how can we create a good second order approximation for a system that responds the same way. So let's go to the next slide. Our goal now is to find M B, and K. We know, let's put down the stuff we know. Natural frequency we found to be 3.51 radians per second. Damping ratio we found to be 0.1097 unitless. We can get B and K right now. How? Square the natural frequency to get K, and then you can use 2 zeta natural frequency to find B. It's a good thought. My question is, because we have a standard form, for our equation. Is this equation in standard form? No, it's not. So I can't do that, though I'd like to. Let's put this thing in standard form real fast. That would be dividing both sides by m. So I get x double dot plus b over m x dot plus k over m x is equal to, now this is really important, it's going to be 1 over m times 10,000. This is standard form, which means, you know, this, once I have it in this form, this is equal to that 2 zeta natural frequency, and this is equal to natural frequency squared. So you're on the right track. We want to use that because I have those two. Problem is I have to put it in. I have 3 unknowns. I have I have 2 equations. Okay. It's kind of tough. I don't know mass. If I can solve for the math, I can solve for these. That would be great. I can't solve for it yet. What can we do? I have an idea. Are you ready? Ready for my idea? You know Hooke's law, right? Like if I apply a force to the end of a spring, usually what's going to happen is going to oscillate until we reach a steady state. So the spring is going to kind of push back, right, on that force, but we're going to displace a little bit. So what we can do to solve this, if I take this equation, K times X steady state has to be equal to 10,000 newtons. Once I, we get all the oscillations out, everything. If I just say at steady state, there's no more acceleration, there's no more velocity. So I'm just looking at steady state. We know what our final value is. So based on that displacement times the spring stiffness is going to give me 10,000 newtons. So therefore K is equal to 10,000 newtons divided by my steady state value, which we said was 0.048 meters. And so our K value should be 208,333 newtons per meter, or you could say 208 kilonewtons per. We're almost done. That's the hard one. Like I'm with you. Like that's where a lot of people mess up is, let me just plug these into there. I know K, I know B, but then they end up saying mass is 1. And if you get a mass of 1, I like pretty much guarantee that's wrong. The math is probably not going to be a nice 1.00. So by putting in steady state, okay, I can't solve that. I need to know one of these values. And so now let's look at it from a steady state standpoint. We can solve for k. Now I can plug in k to find m. So we know that natural frequency is equal to the square root of k over m. Well, natural frequency we found is 3.51 radians per second, equal to square root of 208,333 divided by mass. Therefore, we can find the mass from that equation. So 3.51 squared. And I got a mass of 16,910 kilograms. Now, is that reasonable for the object? Well, the system, again, this is a complex system. Maybe there's actually a lot of different pieces going on. So maybe it's not exactly the mass, but this is a way that we can create a, approximation that can give us the same kind of output. And then lastly, we can find B. So we use the second part of this equation. So B over M, which is 16,910 kilograms, is equal to 2 times zeta, which is 0.1097, multiplied by the natural frequency, which is 3.51 radians per second. Then we're going to solve for B. And I got 13,022 Newton seconds per meter. Now, your homework. I don't know if it's for this homework or maybe the next homework, but you're going to do the same thing with you're going to have a mathematical model. You're going to have a graph. You're going to try to create the mathematical model. One thing you can do is, once I have this, I can really easily check it in Simulate. I create a transfer function. I give it the same input. Does it give me a similar graph? If so, cool, I did it right. That's great. And so you can check, and then we can run different inputs through it as well, and see how it affects it. So we'll be using this quite a bit. It's a good way to create a quick approximate model. Yeah, I'm gonna write some more stuff, but right now it's almost 9:15. So I'd like to kind of give you some time if you want to work on the lab. Is there any questions or take off? You got any questions about here? Yeah, we got the videos too, so maybe get stuck on the homework. All right, I'm gonna end the recording. I'll post the slides. Cool.